Thank you, Laura, and thank you, Ellen. That was a great way to open the day. It's now my honor to introduce our second speaker, Dr. Pete Bisson, who's a retired scientist with the U.S. Forest Service's Pacific Northwest Research Station, and currently is the co-chair of the Science Advisory Panel for the Salmon Recovery Funding Board. After completing his Master of Science and doctorate degrees in fisheries from Oregon State University, Pete began his career as an aquatic biologist for Weyerhaeuser. He later joined the U.S. Forest Service, where his research over the years examined everything from evolution and systematics, fish populations, stream habitat and aquatic food webs, riparian zones, and management issues related to land use impacts on aquatic ecosystems. Pete has served on many advisory panels, held editorial roles and faculty appointments, and received prestigious awards throughout his prolific career, including the Rise to the Future and Jim Siddell Research Achievement Awards from the U.S. Forest Service, the Aldo Leopold Conservation Award from the Federation of Fly Fishermen, and the Award of Excellence and Worthy Coelacanth Awards from the American Fishery Society. With over 100 peer-reviewed publications spanning many decades, Pete's research continues to make a significant contribution to the ongoing efforts to restore freshwater habitats across the Pacific Northwest and beyond. It's a great privilege to have you join us today, Pete, and I pass the mic over to you.
Thank you. Can you hear me okay?
Yes, loud and clear.
Okay, good. Good. I would like to present a sort of a general overview of resilience as it pertains to restoring resilient habitats and restoring resilient salmon populations. These are general things. Many of the later papers will drill down deeper into some of these topics, but I think I wanted to give you an overview of what some of the current thinking might be. Next slide, please. The topics that I'm going to cover are some ecological considerations about salmon habitat in the Northwest, the importance of life history and habitat diversity, some resistance of some implications of restoration for resilience, and some general conclusions. Next slide, please. I'd like to lead off with a famous quote from the conservationist Aldo Leopold, who basically said that if you're going to play around with aquatic ecosystems and with terrestrial ecosystems as well, it's probably a really good idea not to throw away some of the parts, because having that diversity and heterogeneity is important to the landscape and to the streams that flow from it, as well as to the integrity and the resilience of fish populations. Next slide, please. In the Pacific Northwest, we are blessed, and I say blessed very seriously, with a variety of natural disturbances, many of which were ably described by Professor Wohl in the previous talk. These include floods and droughts, landslides, fires, even volcanoes. And the point here is that the frequency and severity of these events is going to vary a lot. Some of them happen quite often. Others are much more rare, and even the really rare ones, like the volcanic eruptions, although they don't happen very often, the legacy of their impacts can last for centuries. Next slide, please. So what we are faced with here naturally is a great diversity of habitat types across the landscape, upon which are overlain impacts of various kinds of human development. And I think that it's important to keep in mind that we're dealing not only with disturbances that are natural in origin, but also ones that are anthropogenic and probably are either impossible or very difficult to reverse in all cases. Next slide, please. Pacific salmon have an extraordinarily high level both interspecific and intraspecific diversity. Uh, uh, One of the things that happened during the evolution of salmon back very far back in the days of ancestral salmon 93 million years ago, their genome underwent an entire duplication. So instead of being diploid, it suddenly became tetraploid, and that has moved in some species away from to more of a diploid situation. But now salmonids in general are considered to be partially tetraploid, which means in effect they've got a lot of DNA, a lot of genetic material that's capable of mutation, and basically promotes genetic new ideas that can be acted upon by natural selection. And this is very important because even though salmon are in difficult straits in some places, not only on the West Coast, but on the East Coast of North America, they have the genetic capacity for resilience. And I'll come back to that more a little bit later in the talk. Next slide, please. Uh, there's an error on the slide, which Jason was kind enough to point out to me. The Fishing Branch River is not in BC. It's part of the Yukon River system. But the graph shows the variability of a population of chum salmon that spawns in this river from a period of time prior to the time that the Yukon Kuskokwim system salmon populations have really started to take a nosedive for reasons that we don't fully understand. But the point here is that this is a pristine watershed. It's an excellent condition, has ample groundwater inputs, and yet its populations, in this case of chum salmon, show a very high level of natural variation. And even if you exclude the outlying years where the run sizes were very high or the years where it was very low, I would guess that the coefficient of variation from year to year for these populations is on the order of 50% or greater. And this was probably indicative of what many natural runs are here in the Pacific Northwest. Next slide, please. An excellent example of this is in the sockeye salmon populations of Bristol Bay. And this is some rather well-known work that Ray Hilborn and his colleagues did in the early 2000s, where he looked at 6 different river systems and where there were inventories of returning sockeye spawning. And the one of the big findings here was that the populations did not rise and fall synchronously. There was a lot of variation. In some years, some populations were up while others were down. And this had the effect of essentially helping to stabilize and buffer the overall runs somewhat. And again, this is another situation which I think is probably widespread in areas where salmon populations aren't extremely depressed. Next slide, please. We'll go back one if you could, please. Thank you. Oh, one ahead. There we go. That's the one. There was a PhD thesis which is not all that well known, which was done over a half century ago by Paul Reimers at Oregon State University, where he was using the tools of the day, which is mainly scale analysis, seining, and otolith analysis, was able to determine that a single population of fall Chinook salmon in a small river on the Oregon coast without a hatchery on it showed 5 distinct life cycle variations ranging from a very short period of time in freshwater all the way down to type number 5, which was essentially imitated a coho salmon life history where juvenile Chinook reared for a full year before emigrating to sea. Now, life cycle type number 3 is the one that has had the highest survival rate, and it's the one that's most commonly associated with with fall run Chinook salmon, where rearing in freshwater lasts for about 90 days or so. Then the fish move to the estuary for extended rearing there and put on a lot of growth, and then enter the ocean later on. But the point here is that Paul felt that it was a way of, by the population, of spreading the risk, if you will, among different life cycles, so that if one life cycle didn't do particularly well in one year, it could be there were others that would help to buffer it. And I think this is an important thing that we need to keep in mind as we attempt to do conservation, not just of habitat, but particularly of salmon populations. Next slide, please. Thank you. Joseph Mertz and his colleagues from California put together an interesting graph on one of the reasons why population recovery has been so difficult, and that is that the ability of the fish to adapt to changes in the environment over time has shifted. In the past, natural disturbances did occur, and they could be quite severe at times, and yet the fish had the ability to respond to those, and it was expressed in their range of conditions, as shown in the upper part of the graph. However, in the lower part of the graph, the acceleration of sediment production from the watersheds, harvest and hatchery practices, which have tended to focus on certain runs and certain timing, have resulted in a disconnect between environmental evolution and animal evolution, and that's resulted in reduced carrying capacity because the fish and the habitat have been so disconnected. Next slide, please. Lee Benda and his colleagues have looked at the rate of disturbance and recovery in river systems in Oregon, and suggested that in headwater streams, and I think this was very well covered by Ellen in the previous talk, do experience often or sometimes severe disturbances, but they tend to be more widely spaced than down in the lower river, where the frequency of disturbances actually is increased. You get more flooding, but the severity of the disturbances, relatively speaking, has been reduced. And so I think that this has implications for what types of restoration will work in headwaters as compared to those which are implemented down in lowland floodplains. Next slide, please. Brooke Penaluna has published a paper looking at the importance of matching restoration to the types of habitat disturbances throughout a catchment, where headwater areas include big but not all that frequent disturbances, such as landslides, down to the mid reaches, where flooding becomes more apparent, and then down to the lower reaches, where flooding actually occurs quite often, and that it's important to make sure that restoration is matched to the type of disturbance and the frequency disturbance in which it occurs as you consider things on a site basis. Next slide, please. And I'm going to show examples of where resilience has proven to occur after restoration. And I'm going to start with probably one of the most apparent examples, and that is the removal of large dams. This is an example of the Elwha River in Washington State. It had two large dams on it that were removed, and the sediment terraces that had built up behind the dams were revegetated afterward. The river then became completely free flowing from its headwaters in Olympic National Park down to its mouth. And the early results there are very encouraging. In fact, we've seen a reawakening of what was formerly isolated headwater rainbow trout population now has begun to exhibit anadromy. And a similar example was found in California by Sarah Hugentobler, finding that the gene for migration timing after removal of a dam in Central California began to be expressed, and we're now seeing a move toward the more historical range of run timing there. So it's possible that some of the genes can be latent and begin to be re-expressed after they're given an opportunity to do so. Next slide, please. We've all seen plenty of examples of road crossings improvement. I think this is a very important first step in the right direction. I hope that the road crossings are engineered in such a way that they don't continue to be choke points for sediment and wood movement downstream. But here we're seeing really an effort, and I think it's correctly directed to give fish access to those areas where they might have been cut off from what were historically important rearing sites, even for the smaller life history variations. Next slide, please. Robin Waples, Tim Beachy, and George Pess have put together a very thoughtful paper on resilience several years ago, and they offer three general suggestions, and I'm going to repeat them here. First, it's to relax constraints on habitat diversity. Here on the left, you see a schematic diagram of a river that's hemmed in by levees. On the right, you see examples where levees have pulled back. It reopens ponds, main stems, side channels, and areas where those life cycle variations can make use of, or even fish that rear in the main stem can make seasonal use of these things during times when they confer either better growth or better survival. Next slide, please. Ellen definitely beat me to the punch on this one. Attenuation of exaggerated disturbance regimes is another important way in which resilience can be promoted in particularly in urbanized areas where a lot of the landscape has been paved over. Storm runoff is channeled very rapidly into streams, and you get much more severe peaks during high stream flow events that building heterogeneity into the drainage system with using things such as reconnecting wetlands and other areas where the stream is basically allowed to breathe by widening out into its floodplain are examples of very good and useful restoration techniques. Next slide, please. And then finally, again, to hammer on the nail of restoring access to headwaters, this is a paper, this is from Waples' paper, that showed that as we've been able to allow fish to get further into headwaters that have been previously blocked by dams, are enabling major life history categories such as stream type or summer Chinook populations and spring Chinook populations from getting into headwater areas, as opposed to basically moving away from those headwater rearing types down to those that rear in the lowlands. So restoring migration pathways is a very important element here. Next slide, please. So in conclusion, I think the general suggestions that I would make were, first of all, to conserve life history diversity. Don't write off small populations or unique life histories. And that's important as we consider our overall attempts to help restore salmon populations. And the second is to make sure that we conserve as much habitat diversity as we can using some of the techniques that were previously described and will be described later in this knowledge sharing workshop, and also to anticipate what the future effects of climate change are going to be. And along those lines, I would like to put in a shameless plug for the first paper after our lunch break today, which is going to provide an example of a tool that can be used to achieve that goal. Next slide, please. So that concludes my presentation here, and I thank you for your attention, and would be happy to answer any questions.
Well, Pete, that was a great talk. As you know, I was anticipating. I think I could just keep you to myself. I've got this list of questions I've been writing. We've got quite a few coming in on our Slido, but I'd like to start with one that I think goes to a comment you were making early on, and it kind of flowed through your conversation around the diversity, the variability. You were talking about the natural landscape is dynamic, and the frequency and severity will vary. But does the climate change effect that we seem to be experiencing now, that the climate scientists are telling us is here and is real, how does that layer over, I think, what you're describing as the natural background in terms of that disturbance regime? And what should we be thinking about? Or should we be thinking about it any differently? Or does it mean what I'm saying is even more important and but the fundamentals don't change?
Thanks, Jason. As an example, to try to get at your question, the climate models are predicting an earlier spring runoff and lower summer flows, and that will make it difficult for fish that rear in headwaters to basically find enough water to work with. One way that we can look for opportunities to address that is to identify those areas that are going to be somewhat resilient to that kind of climate change, and those in particular include spring-fed streams. Spring-fed streams are not going to be quite as affected by the lessening of summer low flows, and they're going to be important areas that will provide for sort of summer refugia for fish that like to stay up there. And yet, at least here in the States, many watershed organizations don't have a particularly strong inventory of the location of major spring systems, and how the fish, and to make sure that the fish can have access to those when they would be necessary. So I think probably some of the other speakers can provide even better examples than I can, but that's one example where you can anticipate the potentially detrimental effects of climate change by providing access to those areas which are going to be naturally resistant to them.
That's great. Thank you for that. My wheels are turning here thinking about what to do about that. I'll turn to the Slido board here. The question that's got the most votes at the moment is the legacy of early industrial forestry practices continues to impact and threaten salmon populations. If there was one single thing we could incorporate into restoration designs to rebuild resilience in our watersheds, what would you recommend?
Okay, for a guy that used to work for a timber company, that's a tricky question. I think the one single thing would be to think very carefully about how you plan your timber sales. I'm not sure if it's the best idea to execute a large number of timber sales over a very large area in a very short period of time. I think it would be more prudent and I realize there are economic arguments pro and con on this, but I think it would be more prudent to plan timber sales that were dispersed more in space and time, so that riparian recovery and hill slope forest recovery can have an opportunity to take place. And I guess I would and add to that a consideration that some rotations be extended to longer periods of time, because I think the scientific evidence is pretty clear now that to grow the really large wood, which is essential to forming the structure in stream channels, you're going to need it's going to take time to do that. And so to make sure that some areas of large wood production exist where it is possible.
So I think to do that's sort of a mix of, I guess, policy, of applied practice, and maybe connecting the way forest landscapes are managed to how they connect to sustainable management and management objectives for the rivers and the aquatic ecosystems.
Yes.
Sounds easy. The question that was kind of floating at the top, it's I think second on our list right now, but it's an interesting one. Over your incredible career studying Pacific salmon, have you encountered any surprises in your research or findings that have shifted your thinking?
That's a really excellent question. I always have a hard time with questions like this. I don't know if there's one single thing, but I think that a long time ago, I had a meeting with some faculty members from University of British Columbia, and one of them was a very wise statistician, and we were talking about would removal of the Snake River dams save Columbia River salmon. And his comment was, there will always be surprises. And that I think that comment really stuck with me, because it sort of suggested that scientists and managers approach restoration with a certain level of humility, which will sort of guide us away from the idea that it's going to be one single thing that we do that's going to fix the problem. And I think if history has shown us anything, that's usually not the case.
We're coming up on our time, but I'm going to just carry this over a little bit longer, if Laura is okay with that. I'll just look across the table. We've got so many questions in our queue here. The next one is, if you could prioritize the 3 most effective actions to maintain life history diversity and salmon population diversity, what would those actions be?
Well, one that I mentioned, these aren't necessarily in order, but one that I mentioned at the outset, and that was restoring access. We need to make sure that fish have access to all the habitat types that they are able to have access. I understand that that's not possible in many situations, that we're just we're stuck with the situation as it is. But where we have opportunities to reconnect formerly occupied habitats, even those that didn't support that many salmon, I think it's worth thinking about. The second is that fish need water, and we can't ever forget that as we move, particularly in light of climate change, as we move forward. We need to be thinking about keeping our streams watered, and watered with continuous surface flows where possible. There are some places that are going to become intermittent during the summer, but we need to keep those surface connections going wherever we can. And that will have implications for things like water withdrawal for agriculture or other human uses. But I think that's the second thing. And the third thing is to not give up on the diversity of life history types. And that isn't so much a habitat issue, but it does have implications for both harvest and hatchery management. And even though that's out of my sandbox a little, I think that's still going to be a real important component of maintaining resilience in salmon.
Well, that's awesome again in terms of scope of a brief answer to a complicated question. I'm going to pick one more before we take a break, and this one's been kind of hovering near the top, and it's got some broad scope, and it's around, does the genetic tetraploidy and the inherent adaptability of salmon mean that you are less concerned about any particular population being lost. Yeah, and the example is compared to another species that might not exhibit these capacities.
Yeah, that's a really good question. I am I think the point I was hoping to make was that salmon have a genetic capacity for resilience, and I think that the message there is that if we give them a chance and basically take our foot off their necks, that we might be pleasantly surprised about how well they can recover, because they do have the genetic building blocks to do that. So if we give them the kind of habitats they need, I think we will have a very good outcome. That's the main point I was trying to make.